So, ideas here. Do you want to do a direct or indirect first?
Direct.
Direct. Okay, I think direct is harder. What are your ideas on a direct proof? We're trying to do something to those three things on the left to conclude T.
Since we're starting out with a non-Q, can we do conjunct on the second one?
Okay, so we've got not Q, that's a premise. And we've got if P, then Q, that's a premise. And then we put those together, indirect reasoning, right? If P is true, Q is true, but Q is false, so it must be that P is false. Right? Or we could take the contrapositive and say not Q implies not P, and then do direct reasoning. Not Q implies not P, therefore not P. Same thing. Either way, we get not P. All right, we're looking good. What do we do with not P? We got one statement we haven't used.
Use conditional equivalence on P or T.
Okay. Oh, I like that. Okay, P or T is a premise. Conditional equivalence. So if we have A implies B, that's logically equivalent to B or not A. Right? We can flip that around. Since we have an or of two things, since we have P or T, we could say that's logically equivalent to the negation of the second thing implies the first thing. Or we could think of it like this. This is logically equivalent to the negation of the second thing implies the first thing. So was one of those going to help us?
The bottom one.
Yeah, this is totally going to help us. So you don't have to do this, but I'll do this anyway. T or P, that's commutativity on statement 4. And this is logically equivalent to not P implies T. Alright, so saying that this is true means that either the conclusion is true or the hypothesis is false. So either T or P. And that's a really nice setup for direct reasoning. Not P and not P implies T. That gets us T. Detachment or direct reasoning. 3 and 6. And we're done.
Didn't you also do disjunctive reasoning or disjunctive simplification?
Mm-hmm.
3 and 4?
Yeah, so we could also, from 3 and 4, since not P is true, we know that P is false. So this is actually false or T, right? And this is because not P is true. So P is false. And then there's a disjunctive simplification, since we have false or something. I don't have my sheet. But since one of these has to be true and false is false, then T has to be true. Let me get to the official. So false or P is equal to P, that's the identity law. That's what we wanted to show. So at least 2 direct proofs we could do. Indirect proof,
Maybe it wouldn't be the whole problem, did we only have to do one?
you only had to do one, yeah.
Oh,
Doing a truth table be seen as an indirect truth?
No. So proof is going out step by step.
Yep.
So an indirect proof, we assume the negation of the conclusion, right? So we have not T. That's an assumption. And then, well, the only thing that talks about T is this statement, P or T. That's a premise. And since not T is true, and P or T is true, and T is false, this tells us P has to be true. So that's again the identity law. And now we can work forward. P implies Q is a premise. Since P is true and P implies Q, we can prove Q. That's direct reasoning. 3 and 4. But here comes the wrench. We know not Q because that's a premise. And that's a contradiction. So by starting with this assumption, we're led to a logical contradiction. That assumption must be wrong. Therefore, T, which is what we were asked to show. So that's an indirect proof. It's still a proof, right? Are you logically using the laws of propositional logic? But we start by assuming the conclusion is wrong and we find a contradiction. And really what we've done here is a direct proof that the negation of T implies false. If we assume not T is true, we can prove Q and not Q, which is false. Since we've proven this, we've also proven the contrapositive, which is logically equivalent, which means not false implies not T, which means true implies T. And since true is true, then T must be true. So it's almost the same as a direct proof. We're just directly proving the contrapositive, basically. So there's a variety of ways to do 5. All right, any other questions on the quiz? Number 3. So here, I'll cheat and make my answer key while we're doing this. For each of the following, indicate whether or not it is a proposition, yes or no. X is greater than 7. Proposition? All right, we'll do a democratic. X squared plus 2x plus 1. Not making a declaration, right? 1 plus 1 equals, if 1 plus 1 equals 2, then the moon is made of green cheese. That's an if-then statement. Those are propositions as long as each piece is a proposition. The moon is made of green cheese. That's a declaration. It has a truth value. There is some integer x for which 2x equals x. Right? We're declaring there is some integer x for which this statement is true. That's a proposition. It's a type of proposition we're going to talk about a lot next week. It's called a quantifier, but it is a declarative statement. Does it make sense? Is that last one a little weird?
No, for the first one.
The first.
one, yeah. Yeah.
X bigger than 7?
Yeah, it didn't say the integer or rational.
Well, okay, I'll give you some wiggle room in there.
Also is correct.
But assuming that X is something that can be compared to 7, that X is not a farm animal, for example, right? Yeah, I don't usually try to be really tricky in these things. But technically, since we didn't say that x is something that's comparable to 7, maybe it's a nonsense statement. So maybe I'll give you some wiggle room in that if that's what you were thinking. Okay, but if it said the integer x is bigger than 7, that would clearly be a proposition. Okay, cool. All right, anything else on here? All right, so we got 5 minutes. Let me just throw a little bit more at you about proofs just to sort of think about over the next 5 days. So let's keep working over the integers, so I don't have to keep saying is an integer. Here's a theorem. If n equals a times b, then a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Let's work over, I just changed my mind. Let's work over the reals. So square roots are meaningful. So if a real number is the product of two other real numbers, a and b, then either a is less than or equal to the square root of n, or b is less than or equal to the square root of n. And this turns out to be true. But it's not necessarily clear how to go about proving this, because we don't really know a whole lot about square roots other than their definition, but nothing that really helps us with propositional logic. Does this theorem seem plausible to you, though?
Yeah.
I mean, if you try some numbers, it kind of makes sense. If you take, 5 and 7 and multiply it, you get 35. What's the square root of 35? Well, it's almost 6. It's definitely smaller than 7, because 7 squared is 49. And it's kind of like, if a gets bigger, then b gets smaller, right? And if a gets so big that it starts to be bigger than the square root, b has flipped over at that point and is less than the square root. But a direct proof of this is perhaps a little elusive, but let's do an indirect proof. So a sidebar here. This is a proposition, right? Okay, to do an indirect proof, we want to assume the negation of this proposition. So De Morgan's theorem, what's the negation of this original proposition? How would we write that out? And, perfect. Right? So the negation of this or is the negation of each term anded together. So our first step of the proof is going to be an assumption a is bigger than square root n and b is bigger than square root n. And that's an assumption. Now, I would write this a little more formally if we had more than 3 minutes. I would say let P be the proposition, A is less than this or B is less than that. And then I would start off by saying not P. That would be my assumption. And then I would write out what not P says. Because at the end we're going to get a contradiction, and then we're going to say, okay, so this must be false, and so the negation of this is true, and that would just be P. But the negation of that will get us our original statement. But let's just look for a contradiction here. Suppose a is bigger than square root n as b is bigger than square root of n. What can we say about a times b?
It's bigger than the product of the square root of n times the square root of n.
Right? We can carry these greater than signs through multiplication as long as things aren't negative. And square roots are not negative, right? We usually assume we're talking about the non-negative square root of a number. And I should probably say A and B are positive, but if A and B are negative, then we know that these statements are true anyway. So if A is bigger than that and B is bigger than that, A times B is bigger than that times that. And what's the square root of n times the square root of n? N. But what's A times B also equal to? It's equal to n. So we've just shown n is bigger than n, and that's a contradiction. So it's you know, with some hand waving to avoid writing details, it's a two-step proof by contradiction. And it's kind of using the idea that if A gets bigger, B's got to get smaller, right? And the only way that this could fail is if A gets big, but B also gets big, and they both kind of get above the square root, and then they're too big because you multiply them together and they're bigger than n. So that's an example of a theorem that proves pretty easily indirectly, not so easily directly. All right, so no class Friday. Homework is due on Monday. Post questions on Discord or find me if you have questions on that. Otherwise, have a good weekend if I don't see you in 224, and we'll keep doing proofs next week.